Tonight on Sleepy Tinfoil Hat, we are going to do something a little unusual. We are going to spend a long, quiet evening looking at the moment that allegedly began everything. The Big Bang. Not as a single tidy event in a textbook, but as a question that physics has been wrestling with for nearly a century, and that, when you actually examine it carefully, turns out to be far stranger and far less settled than the popular accounts would have you believe. Lean back, get comfortable, let your shoulders fall away from your ears. Because the universe, as it turns out, has been keeping secrets, and most of them are still sitting in plain sight in the equations and observations that cosmologists work with every day, waiting for someone patient enough to notice them. Here is the version most of us learned in school. About 13.8 billion years ago, all the matter and energy in the observable universe was concentrated in an unimaginably small, dense, hot point. This point underwent a sudden and rapid expansion. Within fractions of a second, it had cooled enough for the fundamental forces to separate from each other. Within minutes, it had cooled enough for the first atomic nuclei to form. Within a few 100,000 years, it had cooled enough for atoms to capture electrons, releasing the light that we now detect as the cosmic microwave background. Stars formed, galaxies formed, planets formed, life eventually formed, and here we are on a small wet world in the suburbs of a middling galaxy, looking back at the whole sequence and trying to make sense of it. That is the standard story, and it is repeated in countless documentaries and textbooks and museum exhibits with a confidence that suggests the matter is essentially settled. The details may need refinement. The basic picture is taken to be secure. But before we go any further, I want to ask you a small favor. If you find yourself drawn to this kind of slow, careful exploration of cosmic mysteries, the kind that respects both the science and the genuine open questions, please consider subscribing to Sleepy Tinfoil Hat. The channel grows when you tell the algorithm you are here, and the algorithm is the only way new listeners find us. And while you are at it, leave a quick note in the comments telling me where in the world you are tonight. The country, the city, the hour on your clock. I read these. There is something genuinely moving about the map of where this audience is scattered, all listening to the same story at different hours, in different time zones, under different stars. So tell me where you are, and then settle in, because the journey from here will be long and patient, and I hope just strange enough to keep you thinking even as you drift. Now let us return to the official picture and start to gently press on it. The thing that gets glossed over in nearly every popular account of the Big Bang is what the theory actually says about the initial moment. The honest answer is that the theory does not say anything about the initial moment, because the equations break down before we get there. When cosmologists talk about the Big Bang, what they are really talking about is the period after the universe was already very small and very hot, but still describable by known physics. The actual 0 point, the singularity itself, is a place where general relativity returns infinity for the density of matter, infinity for the curvature of space-time, and infinity for the temperature. And infinities in physics are not answers, but signals that the theory has reached the limit of its applicability. The Big Bang, in the technical sense, is not the beginning of the universe. It is the point beyond which our current physics cannot describe what was happening. Everything before that point is, in the strictest sense, unknown, and most of what is presented as the Big Bang in popular accounts is actually the period from somewhere around 10 to the negative 32nd of a second onward, after a hypothetical phase called inflation supposedly smoothed everything out and started the universe expanding in the way we now observe. This distinction matters because it tells us something important about the epistemic situation we are actually in. We have a theory that describes the evolution of the universe with extraordinary precision from a moment slightly after the proposed beginning to the present day. We do not have a theory that describes the beginning itself. We have hypotheses, some of them quite elaborate, but the experimental and observational evidence that would let us choose between them is largely lacking. And the question of what actually happened at the moment of origin, or whether the word origin even applies, is genuinely open. Cosmologists know this. They discuss it freely in their technical papers. But somehow, by the time the science reaches the public through documentaries and popular books, the uncertainty has been smoothed away, and the Big Bang is presented as a known event with a known character. It is not. It is a placeholder for a question we have not yet answered, and the question turns out to be one of the deepest questions human beings have ever asked. The question, in its simplest form, is this: why is there something rather than nothing? Why is there a universe at all, with these particular laws of physics, with these particular fundamental constants, with this particular degree of structure and order, rather than an undifferentiated void or some other utterly different configuration? The Big Bang, as a theory, does not answer this question. It pushes the question back by describing how the universe got from an early hot dense state to its present cooler state, but it does not address why there was an early hot dense state in the first place, or why that state had the specific properties it did, or what, if anything, came before. These questions sit at the boundary of physics and metaphysics, and the honest position is that they remain unresolved despite a century of intense investigation by some of the best minds our species has produced. I want to walk you through, across the parts that follow, what cosmology actually has to say about these questions, what it does not have to say, and what the genuinely strange residues are that the standard story does not adequately handle. Because there are residues, and they are interesting: the flatness of the universe, the horizon problem, the matter-antimatter asymmetry, the unexpected smoothness of the cosmic microwave background, the apparent fine-tuning of the fundamental constants, the dark matter that we have inferred but never directly detected, the dark energy that seems to be accelerating the expansion for reasons no one can fully explain. Each of these is a real anomaly within the standard cosmological model, and each has generated a substantial literature of proposed explanations, none of which has achieved decisive observational confirmation. We are, as a species, in the position of having an extraordinarily detailed map of the universe's history that contains, at several specific points, blank regions marked with question marks and small footnotes, saying that the cartographers are still working on these sections. What I want to do tonight is take you slowly through some of those blank regions. Not because I think I can fill them in, I cannot, and neither can anyone else, at least not yet. But because the blank regions are themselves fascinating, and because understanding what we do not know about the Big Bang is in some ways more revealing than understanding what we do know. The known parts of cosmology are spectacular achievements of human intelligence. The unknown parts are reminders that the universe has not yet finished surprising us, and that the deepest questions about its origin remain genuinely open. The honest cosmologist, when pressed, will admit this. The popular accounts often will not. We are going to spend our time tonight in the gap between these two registers, exploring what it actually feels like to look carefully at the beginning of everything, and to recognize that the beginning is still, in important ways, not understood. The first thing I want you to hold in your mind as we settle into this exploration is the sheer strangeness of the situation we are in. We are, as far as we can tell, the only species on this planet that has developed the capacity to ask questions about its own cosmic origins and to develop technical frameworks for answering them. Every other living thing simply lives, consuming energy and reproducing and responding to its immediate environment without any apparent capacity to step back and wonder where the environment came from. We do this. We have telescopes that can detect light from objects more than 13 billion light years away, light that has been traveling toward us since shortly after the period we call the Big Bang. We have particle accelerators that can recreate energy densities approaching those of the early universe. we have mathematical frameworks of extraordinary sophistication that allow us to model the evolution of the cosmos with precision that would have seemed magical to any earlier generation. And despite all of this, the basic question of why any of it exists at all remains as open as it was when ancient philosophers first asked it. Our tools have grown spectacularly. The fundamental question has not yielded. Tonight, we will not solve it. We will look at it carefully, from several angles, with the kind of patient attention that the question deserves. We will examine the standard cosmological story and the places where it strains. We will look at the alternative frameworks that physicists have proposed and consider why none of them has prevailed. We will think about what it means to live in a universe whose origin we cannot fully explain, and whether the not explaining is a temporary state of affairs that will eventually yield to further investigation, or whether it might be a permanent feature of our cognitive situation. These are not small questions, and I do not propose to handle them lightly, but the handling of them, even partial, even tentative, is one of the deepest pleasures available to a thinking creature on a quiet night. And that is what we are going to do together over the next many hours. Lower the lights, if you have not already. Let your breathing slow. The universe has been here for nearly 14 billion years, according to our current best estimates, and it will outlast all of us by a margin we cannot even begin to imagine. The questions we are about to take up have been asked by every generation since human beings became capable of asking them, and they will continue to be asked long after we are gone. There is no urgency. There is only the careful, patient looking and the willingness to sit with what we find. Let us begin where the official story does not quite begin, which is the moment of inflation. This is the part of the cosmological model that gets glossed over in nearly every popular account, and yet it is, in many ways, the most consequential and the most speculative element of the entire framework. If you have ever watched a documentary about the Big Bang, you have probably heard the word inflation mentioned briefly, perhaps with an animation of the universe expanding rapidly outward before the narrator moves on to more familiar territory. What you may not have been told is that inflation is, in technical terms, an extraordinarily strange addition to cosmology, that it was proposed for very specific reasons that the standard Big Bang model could not handle on its own, and that the evidence for it, while suggestive, is not nearly as decisive as the casual treatment in popular media might suggest. The story of why inflation entered cosmology is itself instructive. By the late 1970s, the basic Big Bang model had been remarkably successful. It explained the cosmic microwave background, which had been discovered in 1965, to a precision that left little doubt that the universe had once been hot and dense. It explained the relative abundances of light elements like hydrogen, helium, and lithium, which matched the predictions of nuclear reactions in the early universe with impressive accuracy. It explained the redshift of distant galaxies, which had been observed by Hubble and others, and which fit naturally with the picture of a universe expanding from a smaller and denser past. The model worked, and it worked well, and most cosmologists by the late 1970s considered the basic framework essentially confirmed. But there were problems, and the problems were not minor. The first problem was the so-called horizon problem. The cosmic microwave background, when observed in different directions across the sky, was found to be astonishingly uniform in temperature. The variation from one part of the sky to another was less than 1 part in 100,000. This was deeply strange, because regions of the sky that are now far apart were, according to the standard Big Bang model, never in causal contact with each other in the early universe. Light, which travels at the maximum possible speed in our universe, simply did not have enough time to traverse from one of these regions to another in the time available since the Big Bang. So how did they end up at exactly the same temperature with such precision when they had no apparent way to communicate with each other and reach thermal equilibrium? the standard model offered no answer. The temperature of the early universe just happened to be uniform everywhere, for reasons that had to be accepted as a brute initial condition. The second problem was the flatness problem. According to general relativity, the geometry of the universe could in principle be curved in any of several ways. It could be positively curved, like the surface of a sphere, in which case parallel lines would eventually converge. It could be negatively curved like the surface of a saddle, in which case parallel lines would diverge. Or it could be flat, in which case parallel lines would remain parallel forever. Observations of the universe consistently showed it to be very nearly flat, within the limits of measurement. This was strange because, in the standard Big Bang model, any small initial deviation from perfect flatness would have grown enormously over the billions of years since the early universe. For the universe to be as flat as we observe it today, it must have been almost unimaginably flat in its early stages, with deviations from flatness no larger than something like 1 part in 10 to the 60th power. This is not the kind of number that seems likely to occur by chance, and the standard model offered no explanation for why the early universe would have started in such an extraordinarily fine-tuned condition. The third problem was the monopole problem, which I will mention only briefly because it is technical, but which mattered to physicists at the time. Certain theories of particle physics that were being developed in the 1970s predicted that the early universe should have produced large numbers of exotic particles called magnetic monopolies. These particles should still be around today in detectable quantities. They are not. They have never been observed, despite extensive searches. So either the theories that predicted them were wrong, or something happened in the early universe that diluted their numbers to the point where they are essentially undetectable. Inflation was proposed in 1980 by the American physicist Alan Guth as a solution to all three of these problems simultaneously. The idea was elegant and audacious. Suppose, Guth suggested, that very early in the universe's history, perhaps around 10 to the negative 36th of a second after the beginning, the universe underwent a brief period of extremely rapid exponential expansion, during which its size increased by a factor of at least 10 to the 26th. This rapid expansion would have stretched any small initial region into a vast space, far larger than the observable universe today. The horizon problem would be solved because the entire observable universe would have originated from a single small region that was in causal contact before inflation began, allowing it to reach thermal equilibrium before being stretched out. The flatness problem would be solved because the rapid expansion would have flattened any initial curvature, just as the surface of a balloon becomes flatter as you blow it up larger. The monopole problem would be solved because the expansion would have diluted any initial density of monopolies to the point of effective non-existence. Inflation was, on its face, a beautiful solution. It elegantly addressed three independent problems with a single mechanism. It made specific predictions, including a particular spectrum of small density variations that should be observable in the cosmic microwave background, and subsequent observations, particularly those made by satellites like COBE and MAP and Planck, confirmed several of these predictions to remarkable precision. The cosmic microwave background does show the kind of small-scale temperature variations that inflation predicted. The universe is flat to within the precision we can measure. The overall structure of the cosmos is consistent with what an inflationary origin would produce. By the early 2000s, inflation had become the standard component of the cosmological model, and it is now treated in textbooks as essentially established. But here is where the picture starts to get strange, and where I want you to slow down and pay attention. Inflation, as a mechanism, requires a specific kind of physics that we do not have direct evidence for. The inflationary expansion is supposed to have been driven by a hypothetical field, often called the inflaton, which had a particular set of properties that allowed it to produce the rapid expansion and then decay into the matter and radiation we observe in the post-inflationary universe. The problem is that no such field has been observed. The inflaton remains entirely theoretical. It is a placeholder, a conceptual entity that does the work the theory needs to be done, but whose actual physical nature is unknown. There are dozens of competing models of inflation, each proposing different properties for the inflaton field, and the available observations do not decisively distinguish between them. The field could be a scalar field of one type. It could be a scalar field of another type. It could be related to the Higgs field. It could be something else entirely. We do not know. Beyond this, inflation has a peculiar consequence that its inventors did not initially anticipate, but that subsequent investigation has made hard to avoid. If inflation happened, it probably did not stop everywhere at once. The mechanism that produces inflation tends, in most versions of the theory, to keep producing it indefinitely in some regions while ending in others. This leads to what is called eternal inflation, in which the inflationary process continues forever in some parts of a vastly larger structure, while local regions, like our observable universe, emerge as bubbles where inflation has ended and ordinary cosmology has taken over. In other words, if inflation happened, then our universe is probably not the only universe, but rather one of an enormous, possibly infinite, ensemble of regions, each with potentially different physical conditions, embedded in a larger inflating substrate that we have no way to observe directly. This is, I want to emphasize, not a fringe speculation. It is a more or less direct consequence of the inflationary model that most cosmologists accept. The multiverse, in this sense, is not something that lies outside mainstream physics. It is what mainstream physics seems to imply if you take inflation seriously and follow its consequences carefully. And yet the existence of these other regions is, by definition, beyond our capacity to verify observationally, because they are causally disconnected from us and always will be. We are in the strange position of having a theoretical framework that predicts a vast structure we cannot see, and that places our entire observable universe within this larger structure as one bubble among many. This raises a question that should make you a little uneasy if you sit with it long enough. If the inflationary multiverse exists, and if different bubble universes within it have different physical conditions, including potentially different values for the fundamental constants of physics, then the question of why our universe has the specific properties it does becomes a question about why we happen to find ourselves in a bubble with these particular properties rather than some other bubble with different properties. The standard answer to this question, which has become increasingly accepted in cosmology over the past 2 decades, is the anthropic principle. We find ourselves in a universe with these properties because these are the properties compatible with our existence as observers. Universes with different properties might not produce stars or planets or chemistry or life, and so there would be no observers in them to ask why the properties were what they were. We are here because we can be here. The properties of our universe are what they are because, if they were different, we would not exist to notice. There is something deeply unsatisfying about this kind of explanation, and many physicists have resisted it. It feels, to many serious thinkers, like a form of giving up, a way of avoiding the question of why the universe has its specific properties by appealing to a selection effect rather than to a deeper underlying reason. But it also feels, to many other serious thinkers, like the only honest answer available given the structure of inflationary cosmology. If inflation produces a vast ensemble of bubble universes with varying properties, then anthropic reasoning is not optional. It becomes the natural framework within which to understand why our particular bubble has the properties we observe. What I want you to take from this part of our exploration is not a confident position on whether inflation is correct or whether the multiverse exists. I do not have such a position, and neither does anyone else who is being honest about the state of the evidence. What I want you to take is a more accurate sense of where contemporary cosmology actually stands. The field has assembled, over the past century, a remarkably detailed account of the universe's evolution from a very early hot dense state to the present day. That account is supported by extensive observational evidence and represents one of the great achievements of human intellectual history. But the theoretical framework that produces this account also seems to imply, almost as a side effect, the existence of a vastly larger structure that we cannot observe, and the question of what to make of this larger structure remains genuinely open. The official cosmology of our time has, embedded in it, an enormous question mark, and the question mark is not a small detail. It is a fundamental part of the picture that the popular accounts tend to gloss over, and that anyone who wants to understand the actual state of the field needs to take seriously. So as you let yourself settle deeper now, hold this image gently, a vast ocean of inflating space, stretching forever in every direction, in which bubble universes form and grow and develop their own internal physics. Most of these bubbles, if they exist, contain conditions hostile to anything we would recognize as life. A small fraction contain conditions that allow stars and planets and chemistry to develop. Within an even smaller fraction of these, observers eventually emerge who can ask questions about their own origins. We may be in one such bubble. We may be the only ones in our bubble who have developed the technology to ask these questions, or we may not be, and there may be other observers elsewhere doing the same work. The picture is staggering when you allow yourself to actually contemplate it, and it is, according to our current best theories, the most likely description of the situation we find ourselves in. We do not know if it is true. We have no way to know if it is true. But it is what the mathematics keeps suggesting, and the mathematics has been right often enough that we cannot simply dismiss what it is telling us. Tonight I want to take you deeper into one of the strangest features of the universe we actually inhabit, regardless of whether the inflationary multiverse turns out to be real or not. I want to talk about the apparent fine-tuning of the fundamental constants of physics. This is a topic that physicists discuss with some discomfort, because it sits in an uncomfortable place between empirical observation and philosophical interpretation, and because the implications of taking it seriously are unsettling regardless of which interpretive direction you go. But it is one of the most genuinely interesting features of contemporary cosmology, and any honest exploration of how the universe came to be the way it is has to spend serious time with it. The basic observation is this: the laws of physics, as we currently understand them, contain a number of fundamental constants whose values are not predicted by any deeper theory. These include the strength of gravity, the strength of the electromagnetic force, the strength of the strong and weak nuclear forces, the masses of the various fundamental particles, the cosmological constant that governs the rate of cosmic expansion, and several others. The total count, depending on how you organize the categories, is somewhere between 20 and 30 independent numbers. These numbers are simply observed to have the values they have. We measure them, we plug them into our equations, and the equations then produce predictions that match further observations to extraordinary precision. But the values themselves, the specific numbers, are not derived from any underlying principle. They are inputs to our theories rather than outputs of them. Now here is where it gets strange. When physicists examine what would happen if these constants had slightly different values, they discover that the universe would in many cases be radically different from the one we observe, and in most cases would be incapable of supporting any complex structure at all, let alone life. The strength of gravity, for instance, has a specific value that allows stars to form, burn for billions of years, produce heavy elements through nuclear fusion, and eventually disperse those elements into space when they die. If gravity were significantly stronger, stars would burn through their fuel too quickly to support the development of planets and life. If gravity were significantly weaker, gas clouds would never collapse densely enough to form stars at all. The window of values that produces a universe capable of evolving stars like our Sun is narrower than the full range of mathematically possible values by an enormous margin. The strength of the strong nuclear force, which holds atomic nuclei together, presents a similar situation. If this force were a few percent stronger, the universe would have produced essentially no hydrogen, because all the protons would have bound into helium during the early phases of nucleosynthesis. Without hydrogen, there would be no water, no organic chemistry, no stars that burn the way our Sun burns. If the strong force were a few percent weaker, no atomic nuclei larger than hydrogen would be stable, and the universe would consist of nothing but hydrogen gas, with no chemistry beyond the simplest possible. The window of values that produces a universe with diverse chemistry is again much narrower than the full range of mathematically possible values. The cosmological constant, which governs the rate at which the universe's expansion is accelerating, presents perhaps the most extreme example. The observed value of this constant is something like 10 to the negative 120 in the units that physicists naturally use for it. This is an extraordinarily small number, but it is not zero. If it was zero, the universe would not be accelerating its expansion. If it was significantly larger than it is, the early universe would have expanded so quickly that gravitational structures like galaxies and stars would never have had time to form, leaving behind a cosmos of thinly distributed matter with no complex structure anywhere. The fact that the cosmological constant has a value small enough to allow structures to form, but not so small that the universe has stopped expanding, is, by any reasonable measure, an extraordinary coincidence. The window of acceptable values is, in this case, vanishingly small compared to the range that physical theory might allow. There is a famous calculation, often attributed to physicists Brandon Carter and Bernard Carr, that attempts to estimate the overall improbability of a universe that supports complex structure. The estimate involves taking the various fine-tuning windows, multiplying their probabilities together, and asking what fraction of randomly chosen universes would have a combination of constants compatible with the development of stars, planets, chemistry, and eventually, observers. The numbers that come out of these calculations are not small in any everyday sense. They are inconceivably small. They are numbers like 10 to the negative 229, or even smaller, depending on which fine-tunings you include and how you weight them. To put this in perspective, the number of fundamental particles in the observable universe is somewhere around 10 to the 80. The numbers we are talking about for fine-tuning are smaller than that by margins that beggar comprehension. If our universe were chosen at random from the space of mathematically possible universes, the probability of getting one with conditions compatible with our existence would be smaller than the probability of randomly selecting a single specific atom from among all the atoms in the observable cosmos repeatedly for billions of selections in a row. This is a real result. It is not a creationist talking point or a religious argument. It comes out of mainstream theoretical physics, and the leading physicists of our time, regardless of their personal philosophical commitments, take it seriously as a phenomenon that needs explanation. The disagreement is not about whether the fine-tuning is real. The disagreement is about what it means and how it should be explained. There are several main interpretive options on offer, and I want to walk you through them carefully, because each one has interesting consequences, and none of them is obviously correct. The first option is what we might call the brute fact interpretation. According to this view, the fine-tuning is real, but does not require explanation. The fundamental constants have the values they have. Those values happen to be compatible with the development of complex structure, and any further question is misguided. The universe simply is what it is, and demanding an explanation for its specific properties is like demanding an explanation for why one particular ticket won a lottery. Someone had to win, and asking why it was this person rather than another is to misunderstand the nature of probability. This is the most deflationary position, and it has the virtue of not requiring any speculative additions to the theoretical framework. Its disadvantage is that it feels, to many thinkers, like an evasion. The fine-tunings are not just one or two surprising values. They are dozens of independent improbabilities that all line up in a particular direction, and waving them off as a cosmic coincidence strains intuition past its breaking point. The second option is the multiverse interpretation, which we touched on in the previous part. According to this view, the fine-tuning is explained by the existence of a vast ensemble of universes with varying properties. Most of these universes are sterile or simple, but a small fraction have conditions compatible with complex structure, and we, by necessity, find ourselves in one of these. The fine-tuning is real, but it is a selection effect rather than a cosmic accident. We observe a fine-tuned universe because only fine-tuned universes contain observers. This interpretation has the advantage of fitting naturally with inflationary cosmology and string theory, both of which suggest that ensembles of distinct universes are theoretically possible. Its disadvantage is that the other universes are, by their nature, unobservable, and the multiverse therefore explains the fine-tuning by appealing to entities that we cannot directly verify. Critics of this approach argue that it is a violation of the principle of parsimony, multiplying universes beyond necessity to avoid drawing conclusions from the fine-tuning of the one universe we can actually observe. The third option is the design interpretation. According to this view, the fine-tuning suggests that the universe was, in some sense, configured deliberately to produce conditions compatible with life and observers. This interpretation has obvious affinities with traditional religious thought, but it does not have to be presented in religious terms. Some physicists and philosophers have proposed naturalistic versions of this idea, including the suggestion that the universe is some kind of simulation, or that it is the product of an unknown selection process within a deeper layer of reality, or that it has properties of self-organization that we do not yet understand, and that bias outcomes toward complexity. The advantage of design interpretations is that they take the fine-tuning seriously as evidence rather than dismissing it as coincidence. The disadvantage is that they introduce explanatory entities that are themselves unexplained, and they can end up pushing the fundamental question one step further back without actually resolving it. If the universe was designed, what designed the designer? The fourth option, and the one I find most interesting, is what we might call the necessitation interpretation. According to this view, the fine-tuning is real, but only apparent, because the constants are not actually free parameters that could have taken other values. They are, in this view, determined by some deeper principle that we have not yet discovered, and the appearance of fine-tuning is an artifact of our incomplete theoretical understanding. If we had a complete theory of physics, we would see that the constants must have the values they have, that any other values would be mathematically inconsistent or physically impossible, and that the fine-tuning would dissolve into a recognition that the universe could not have been otherwise. This is the position favored by many physicists who hope for a final theory that will derive the fundamental constants from first principles. Its advantage is that it preserves the possibility of full scientific explanation. Its disadvantage is that no such final theory currently exists, and the search for one has been ongoing for many decades without success. We may eventually discover that the constants are determined by deeper principles, or we may discover that they are not, and the question is currently open. I want to emphasize that none of these interpretive options has achieved decisive support, and that thoughtful physicists currently disagree about which is most plausible. The fine-tuning of the fundamental constants is one of the genuinely open problems in contemporary cosmology, and the various proposed solutions all have serious difficulties. What is not in dispute is that the fine-tuning itself is real. The universe could have had different fundamental constants, and almost any other set of values would have produced a universe radically different from the one we observe. In most cases, a universe incapable of supporting any complex structure at all. The fact that we exist in a universe with the specific values that allow our existence is, depending on which interpretation you favor, either a brute fact, a selection effect within a multiverse, a sign of design, or evidence of an undiscovered deeper principle. Choosing among these options is not really a scientific question at the moment, because no observation we can currently make would distinguish between them. It is a question of which kind of explanation you find most plausible given the available evidence, and reasonable thinkers disagree. What I want to leave you with as we move toward the next part of our exploration is a sense of the genuine strangeness of the situation we find ourselves in. The universe we inhabit is, by any reasonable measure, an extraordinarily improbable kind of universe. Its fundamental constants are configured in ways that allow for the development of stars, planets, chemistry, biology, and consciousness, and the configuration is precise enough that small changes in any of several independent parameters would have produced a sterile or simple cosmos with nothing of interest in it. We do not know why this is. We have several competing explanations, none of which is decisively supported, and the question of how to interpret the fine-tuning remains one of the most contested issues in theoretical physics. The popular accounts of cosmology often skip over this entirely, presenting the universe's properties as if they were straightforwardly given by physics. They are not. They are mysteries within physics. Mysteries that the field has not yet resolved, and they are mysteries that touch the deepest questions human beings have ever asked about why anything exists at all, and why it has the form it does. So as you let your thoughts drift now, hold this in mind. Every breath you take, every beat of your heart, every thought that passes through your mind, depends on a configuration of physical law so specific that the probability of stumbling into it by chance is essentially zero. You are here because the universe is configured in a way that allows you to be here, and the configuration is improbable to a degree that staggers comprehension. Whether this means anything beyond itself is a question we have not answered. But the configuration is real, and you are its product, and the night you are spending listening to this voice exists because, somewhere in the chain of cosmic causation, the constants of physics fell into a window of values narrow enough that something like you became possible. Claude responded. There is another puzzle I want to bring into our exploration tonight. One that may seem at first to be technical and remote, but that turns out to touch the SAM. There is another puzzle I want to bring into our exploration tonight. One that may seem at first to be technical and remote, but that turns out to touch the same deep questions about why the universe is the way it is. I want to talk about matter and antimatter, and about the fact that you are made of one and not the other, and about why this distinction, which sounds like a curious detail, is actually one of the most unresolved problems in modern physics. Because the universe should not, according to our best theories, contain any matter at all. The fact that it does, the fact that you exist, the fact that the chair you are sitting in exists, the fact that there are stars and planets and galaxies rather than empty space full of radiation, is a phenomenon that no current theory adequately explains. Let me lay out the basic situation. Particle physics has established, through extensive experimental verification, that every particle of matter has a corresponding antiparticle with opposite properties. Electrons have positrons, protons have antiprotons, neutrons have antineutrons. The two kinds of particle are mirror images of each other in specific technical senses, and when a particle of matter encounters its antiparticle counterpart, the two annihilate completely, converting their entire mass into energy in the form of high-energy photons. This is not speculation. It has been observed in particle accelerators thousands of times. The annihilation is total. The energy release follows Einstein's famous equation precisely, and the process is one of the most thoroughly verified phenomena in modern physics. Here is the puzzle. According to our current understanding of how particles are produced from energy, every interaction that creates matter should create exactly equal amounts of matter and antimatter. When energy converts to particles, it does so in pairs, one particle of matter for each particle of antimatter, in carefully balanced quantities. This has been confirmed in countless experimental contexts. Particle accelerators produce matter and antimatter in equal proportions whenever they generate new particles from collision energy. The symmetry between the two is, as far as we can tell, essentially perfect at the level of individual interactions. But the universe is not symmetric between matter and antimatter. It is, as far as we can observe, almost entirely composed of matter. Antimatter exists, and we can produce it in laboratories and detect it in cosmic rays, but it is rare, present in trace quantities compared to the matter that dominates the cosmos. There are no large structures made of antimatter that we have ever detected, no anti-stars, no anti-galaxies, no regions of space where antimatter dominates. If such regions existed, we would expect to see characteristic high-energy radiation at the boundaries where antimatter encountered matter and annihilated, and we do not see this radiation. The observable universe appears, to the limits of our ability to investigate it, to be made of matter, with antimatter present only as a minor and transient component. This is genuinely strange. If matter and antimatter were produced in equal quantities in the early universe, as our theories of particle physics seem to require, then they should have annihilated each other completely as the universe cooled. The result should have been a cosmos containing essentially no matter at all, just a vast diffuse background of photons left over from the annihilation, with perhaps a tiny residue of either matter or antimatter due to small statistical fluctuations. The universe we should have, according to our best theories, is empty. The universe we actually have contains stars and planets and people. Something happened, somewhere in the early history of the cosmos, that broke the symmetry between matter and antimatter and left a small excess of matter behind to form everything we see. The mechanism that did this is one of the great unsolved problems of modern physics, and the solutions that have been proposed are all unsatisfactory in various ways. The Russian physicist Andrei Sakharov in 1967 laid out 3 conditions that any successful explanation of the matter-antimatter asymmetry would need to satisfy. The early universe must have contained interactions that violated certain symmetries between matter and antimatter. The universe must have been out of thermal equilibrium during the relevant period, and certain processes must have allowed for the violation of conservation laws that would normally keep the matter and antimatter quantities balanced. These conditions, known now as the Sakharov conditions, are widely accepted as the necessary criteria for any solution. The problem is that, while particle physics has identified some processes that satisfy these conditions, none of them are strong enough to produce the asymmetry we actually observe. The standard model of particle physics, which is our current best theory of the fundamental constituents of matter, includes some symmetry violations that could in principle contribute to the matter-antimatter asymmetry. There is a phenomenon called CP violation, which has been observed in certain decays of particles called kaons and B mesons, that does indeed treat matter and antimatter slightly differently. But the magnitude of CP violation in the standard model is many orders of magnitude too small to account for the observed asymmetry between matter and antimatter in the universe. By the most generous estimates, the standard model can account for perhaps 1 part in 10 billion of the actual asymmetry. The remaining factor of 10 billion or so has to come from somewhere else, from physics that we have not yet discovered, from interactions that occurred in the early universe that we cannot recreate in our current accelerators, from mechanisms that exist in our theoretical models, but for which we have no direct experimental evidence. There are several proposed extensions of the Standard Model that could in principle resolve this problem. Theories involving additional Higgs fields beyond the one that has been observed, theories involving supersymmetric partners of the known particles, theories involving the existence of heavy neutrinos that decay asymmetrically into matter and antimatter, theories involving exotic phase transitions in the early universe. Each of these proposals has its proponents and its critics. None has been confirmed by direct experimental evidence. The matter-antimatter asymmetry remains, after decades of intensive theoretical and experimental work, one of the major open problems in physics, and the universe's existence depends on a mechanism that we have not yet identified. Now I want you to sit with this for a moment, because the implications are quite striking when you actually take them in. The fact that you exist, that there are atoms making up your body and your environment, depends on a tiny imbalance that arose somewhere in the first fraction of a second after the Big Bang. The numbers are usually given as something like 1 extra particle of matter for every billion or so matter-antimatter pairs that were produced and annihilated in the early universe. Out of every billion pairs of particles, the matter and antimatter members annihilated each other and produced photons, and 1 extra matter particle was left behind. That tiny residue, 1 part per billion, is what makes up everything we see today. The stars in the night sky, the planets, the people, the entire material substance of the cosmos are all composed of the leftover matter from a vast cosmic annihilation that erased nearly everything that was originally produced. This is, by any measure, an extraordinary thing to contemplate. The universe, in some sense, is a vast tomb of annihilated antimatter, with our entire material existence consisting of the small fraction of matter that escaped the annihilation due to a mechanism we do not yet understand. Every atom in your body is a survivor of a process that destroyed 1,000 times its mass in matter-antimatter annihilation in the first moments of cosmic history. The photons that resulted from those annihilations are still around, by the way, spread throughout the universe as the cosmic microwave background, the afterglow of the Big Bang that we now detect with sensitive radio telescopes. When you look up at the night sky and feel the dark coldness of space, you are looking at, among other things, the radiation left over from the Great Annihilation, the cooled remnant of the energy that was released when most of the early universe's matter and antimatter destroyed each other. I want to draw a connection here to the broader theme we have been developing. Throughout this exploration, I have been pointing to features of the universe that cosmology describes precisely, but does not fully explain. The fine-tuning of the fundamental constants, the apparent need for inflation, the matter-antimatter asymmetry. Each of these is a place where our theoretical framework requires an additional ingredient that we cannot derive from deeper principles, and each of these ingredients turns out to be essential for the existence of the world we observe. The cumulative effect of these unexplained features is, I think, important to recognize. Modern cosmology is not a complete account of why the universe is the way it is. It is a precise description of how the universe evolves once certain initial conditions and certain parameter values are given. But the initial conditions and parameter values themselves are largely mysterious, and they are the things that actually determine why the universe contains anything. Interesting at all, there is a particular sense in which this situation should make us humble about what we know. We have constructed theories of remarkable predictive power that work to many decimal places of precision in their proper domains. Within those domains, our knowledge is extraordinary, and the technological achievements that derive from our knowledge are spectacular. But the boundaries of those domains are clearly visible if you look for them. And at the boundaries, our theories simply hand off the explanatory work to inputs that we cannot independently justify. Why is the universe inflating in the way it does? We do not know. Why are the fundamental constants what they are? We do not know. Why is there matter at all, rather than nothing? We do not know. Each of these questions sits at the edge of physics, and each of them is genuinely open, and each of them touches something fundamental about the nature of the cosmos and our place in it. There is one more aspect of the matter-antimatter problem that I want to mention before we close this part of our exploration, because it points towards something even stranger. There are some theoretical approaches that suggest the matter-antimatter asymmetry might not be a feature of the universe as a whole, but only of the part of the universe that we can observe. If the early universe, during inflation or some related period, separated into regions of matter dominance and regions of antimatter dominance, and if those regions are now causally separated from each other by vast distances, then we might be living in one of the matter-dominated regions while other regions exist that we cannot observe. This is again not crackpot speculation. It is a serious theoretical possibility that has been explored in the technical literature. Its implications are interesting because it would mean that the apparent asymmetry of the cosmos is local rather than global, and that the deeper structure of the universe might preserve the symmetry between matter and antimatter that our particle physics suggests should exist. Whether this is true or not, we do not know. The regions of antimatter dominance, if they exist, would be far enough away that any radiation from boundary annihilations would not have reached us yet, or would be diluted to the point of undetectability, or would be hidden behind the horizons that limit what we can see. We are, in other words, in a position where we cannot easily test whether the universe is fundamentally asymmetric in its matter content, or whether the asymmetry is just a feature of our local neighborhood. This is yet another instance of the pattern we have been observing throughout this exploration. The universe contains features that our theories can describe but cannot fully explain, and the explanations that have been proposed often involve entities or regions that we cannot directly verify, leaving us in a state of theoretical commitment without empirical confirmation. So, picture this, as you let your awareness soften, a cosmos in which nearly all the matter that was originally produced has been destroyed, leaving behind only a thin sediment of survivors. The survivors have organized themselves over billions of years into stars and galaxies and planets, and on at least one of those planets, into living things capable of contemplating their own origin. The mechanism by which the survivors escaped the Great Annihilation is unknown. The reasons why the universe was configured to allow the survival in the first place are unknown. The deeper structure of the cosmos beyond our observable region is unknown. And yet here you are, a survivor of survivors, descended from atoms that emerged from the early universe through a process that we cannot yet account for, listening to a voice describing the very puzzle that allowed your existence. The night is large, and the questions it raises are deep, and the careful sitting with them is itself a kind of communion with the strangeness of being here at all. There is another dimension of cosmic strangeness I want to bring into our exploration tonight, and it concerns something that surrounds you at this very moment. There is another dimension of cosmic strangeness I want to bring into our exploration tonight, and it concerns something that surrounds you at this very moment, that fills the universe to a degree that vastly exceeds the amount of matter we have been discussing, and that we have never directly detected despite decades of increasingly sophisticated effort. I want to talk about dark matter and dark energy, the two enormous unknowns that together make up roughly 95% of the contents of the cosmos. The ordinary matter that constitutes you, the planet you live on, the stars you can see in the night sky, and everything else made of atoms, accounts for less than 5% of what is out there. The remaining 95% is something else, something we have inferred indirectly from its effects on the things we can observe, but whose actual physical nature remains, in significant ways, a mystery. Let me start with dark matter, because it is the older of the two puzzles, and it is, in some respects, the more straightforward, though calling either of these phenomena straightforward is a generous use of the term. The story begins in the 1930s with a Swiss astronomer named Fritz Zwicky, who was studying the Coma cluster a large cluster of galaxies. Zwicky measured the velocities of the galaxies in the cluster and found something deeply puzzling. The galaxies were moving so fast that, given the visible mass of the cluster, they should have been flying apart. The gravitational pull of the visible matter was nowhere near strong enough to hold the cluster together at the observed velocities. By all rights, the cluster should not exist, yet it clearly did exist, observed and photographed and mapped in detail. Zwicky concluded that there must be a great deal of unseen mass in the cluster, providing the additional gravitational pull required to hold everything together. He called this hypothetical missing mass dunkel materie, dark matter, and his work was largely ignored for several decades, treated as an anomaly that would presumably be resolved by better observations of the visible matter. It was not resolved by better observations. It got worse. In the 1970s, the American astronomer Vera Rubin made detailed measurements of how stars move within individual galaxies, and she found the same kind of problem on a much smaller scale. Stars at the outer edges of galaxies were moving far too fast to be held in place by the visible mass of the galaxies they belonged to. Galaxies, like clusters of galaxies, appeared to contain enormous quantities of unseen mass, and the unseen mass was distributed in a way that affected the rotation of the galaxies themselves. Rubin's work was harder to ignore than Zwicky's had been, because it involved observations of the same kind of object, ordinary spiral galaxies, in many independent cases, and the pattern was consistent across the sample. Something was there, exerting gravitational influence that we could not see by any direct means. Subsequent decades of observation have only deepened the mystery. Dark matter has been inferred from the motions of stars within galaxies, the motions of galaxies within clusters, the gravitational lensing of light by intervening masses, the patterns of large-scale structure formation in the cosmos, and the precise temperature variations in the cosmic microwave. Background. All of these independent lines of evidence converge on roughly the same conclusion, which is that there is approximately 5 times as much dark matter in the universe as there is ordinary matter, and that the dark matter is distributed in vast halos around galaxies and through the spaces between, them providing the gravitational scaffolding around which ordinary matter has organized itself over cosmic history. The dark matter does not interact with light. It does not emit, absorb, or reflect any electromagnetic radiation that we have been able to detect. It interacts gravitationally with everything else, and that is essentially the only way we know it is there. What is dark matter actually made of? Here is where the story becomes embarrassing for physics. After more than 50 years of intensive theoretical and experimental work, we still do not know. The leading candidates have, for most of this period, been hypothetical particles called weakly interacting massive particles, or WIMPs. The idea is that there exists a class of particle, predicted by extensions of the standard model of particle physics, that interacts with ordinary matter through gravity and through the weak nuclear force, but not through electromagnetism. Such particles would be invisible to us in any direct sense, would have been produced in large quantities in the early universe, and would have settled into the gravitational halos around galaxies that we infer from the motion of visible matter. The theoretical framework was elegant, the prediction was specific, and the search seemed promising. The search has not succeeded, despite increasingly sensitive experiments conducted in deep underground laboratories around the world, despite particle accelerators specifically designed to look for the production of dark matter particles in high-energy collisions. Despite years of work by hundreds of physicists, no WIMP has been definitively detected. The space of possible WIMP properties has been steadily narrowed by null results, and many of the originally favored regions of parameter space have now been excluded. The leading candidate for dark matter for the past half-century has, for all practical purposes, failed its experimental tests, and the field has been forced to consider alternatives. The alternatives are interesting and varied. Axions, hypothetical particles originally proposed for unrelated reasons in particle physics have become a major candidate, and dedicated experiments are now searching for them. Sterile neutrinos, hypothetical heavy cousins of the ordinary neutrinos, are another possibility. Primordial black holes, formed in the early universe rather than from the collapse of stars, have been seriously revisited as a candidate, particularly in light of the gravitational wave detections from black hole mergers. There are also more exotic proposals, including modified theories of gravity that would eliminate the need for dark matter entirely by changing the laws of physics at large scales, and theories involving entire sectors of unknown particle physics that interact with ordinary matter only through gravity. Each of these proposals has its advocates and its critics. None has achieved decisive observational confirmation. The actual identity of dark matter remains, after half a century of dedicated search, an open question. Now let me bring in the second great unknown, which is dark energy. This one is even stranger, and it is more recent, dating only to the late 1990s, when two independent teams of astronomers studying distant supernovae announced that the expansion of the universe was not slowing down due to gravity, as had been expected, but was actually speeding up. This was, at first, almost universally disbelieved. The observation contradicted the prevailing theoretical expectation in a fundamental way, and the implications were so strange that many physicists initially assumed there must be some error in the analysis. But the observations held up, and they were confirmed by additional studies using different methods, and within a few years, the cosmological community had reluctantly accepted that the universe's expansion was accelerating. The 2011 Nobel Prize in Physics was awarded to the leaders of the two teams, recognizing the discovery as one of the most important in modern cosmology. The acceleration requires a driving force, and the force has been called dark energy, though the name is mostly a placeholder for our ignorance. Whatever it is, dark energy makes up approximately 70% of the total energy content of the universe, with dark matter making up about 25% and ordinary matter making up the remaining 5%. The dark energy fills space uniformly, so its effects only become important on the largest scales, where the cumulative push of dark energy across vast volumes overwhelms the gravitational pull of matter. As the universe expands and matter becomes more diluted, dark energy becomes proportionally more important, which is why the acceleration has only become significant in the relatively recent cosmic past, within the last few billion years. What is dark energy? Here, our ignorance is even more profound than with dark matter. The simplest theoretical option is that dark energy is the cosmological constant, a constant energy density of empty space itself, with a value that has been roughly the same throughout cosmic history. This idea originated with Einstein, who introduced the cosmological constant into his equations of general relativity for unrelated reasons, then abandoned it as his greatest blunder, only to have it returned decades later as the favored explanation for cosmic acceleration. The cosmological constant fits the observations reasonably well. The trouble is that, when we try to calculate what the cosmological constant should be from quantum field theory, the theoretical prediction comes out wrong by approximately 120 orders of magnitude. This is not a small discrepancy. It is the worst theoretical prediction in the history of physics, off by a factor of 1 followed by 120 zeros. Either our calculations are missing some enormous cancellation effect that nobody has yet identified, or the cosmological constant is not actually the right description of dark energy and something else is going on. The alternatives include various proposals for dynamical dark energy, in which the energy density changes with time according to some underlying field whose properties we have not yet identified. There are proposals involving modifications to general relativity at cosmological scales, which would change the relationship between matter and the geometry of space-time in ways that might mimic the appearance of dark energy without requiring it to be a real component of the universe. There are proposals involving extra dimensions of space, in which the apparent acceleration is a side effect of the geometry of higher dimensional spaces, in which our familiar three-dimensional universe is embedded. Each of these proposals, like the proposals for dark matter, has its supporters and its difficulties. None of them has been confirmed. I want to step back now and take stock of where this leaves us. Modern cosmology has assembled a detailed and observationally well-supported picture of the universe's evolution over the past 13.8 billion years. The picture is precise enough that we can predict, to within a fraction of a percent, the temperature of the cosmic microwave background, the abundances of light elements produced in the early universe, the patterns of large-scale structure that we observe today, and the rate at which the universe is currently expanding. These predictions are not approximate. They match observation with extraordinary precision, and the matching is one of the great achievements of modern science. But the picture is built on foundations that include three enormous unknowns. The mechanism that drove inflation in the early universe is not known. The composition of the dark matter that gravitationally dominates galaxies is not known. The nature of the dark energy that is currently accelerating the cosmic expansion is not known. Together, these three unknowns account for the great majority of the actual physical content of the cosmos, and the precise theory we have built describes the consequences of these unknowns without explaining what the unknowns themselves are. There is something almost vertiginous about this situation when you sit with it. The universe we live in is mostly composed of substances and processes whose nature is opaque to us. The 5% of the cosmos that we understand, the ordinary matter made of atoms and the radiation that interacts with it, has been studied with such intensity and modeled with such precision that we sometimes lose sight of how unrepresentative this 5% really is. The other 95%, which dominates the dynamics of the universe at every scale, from individual galaxies to the cosmos as a whole, is a domain of inference and conjecture rather than direct observation. We know it is there because we see its effects. We know roughly how much of it there is because the gravitational and dynamical evidence is consistent across many independent measurements. We do not know what it actually is, and despite decades of dedicated effort, we have not yet identified the underlying physics in a way that experiment has confirmed. This should not, I want to emphasize, lead to despair about the scientific enterprise. The very fact that we know how much we do not know is itself a significant achievement. Earlier generations did not have the precision to recognize the existence of dark matter and dark energy, and so they did not have the luxury of being puzzled about them. We do, and the puzzlement is a sign that our investigation has reached a point where the next questions can be clearly formulated, even if they cannot yet be answered. There is real progress in this. The puzzles of dark matter and dark energy are not random gaps in our knowledge. They are specific, well-defined problems with measurable parameters, and they have driven the development of new instruments and new theoretical approaches that are slowly narrowing the space of possibilities. The questions may eventually be answered, perhaps within our lifetimes, perhaps not. The work continues. What I want you to hold from this part of our exploration is a more accurate sense of the relationship between scientific knowledge and scientific ignorance. We sometimes speak as if science gives us a complete picture of the universe, with only minor details to be filled in. The actual situation is closer to the opposite. Science gives us an extraordinarily detailed picture of a small portion of what is out there, and it gives us reasonable but incomplete inferences about the much larger portion that we have not yet directly investigated. The universe is mostly invisible to us, mostly dark, mostly composed of things whose nature we are still trying to determine. We live, in a literal sense, in a small island of comprehension, surrounded by vast oceans of physical reality whose properties we are still struggling to understand. The night sky, when you look up at it, is mostly empty of the things we have managed to identify. The dark spaces between the stars are not really empty. They are filled with substances and energies that exceed everything we can see by a factor of 19 to 1, and we are still working out what they are. Tonight I want to take you into a question that has haunted physics for nearly a century, but that rarely makes it into popular accounts of the Big Bang in any serious form. The question concerns the nature of time itself, specifically whether the time we experience and measure has anything to do with the time that appears in the equations of cosmology, and whether the apparent direction of time, the flow from past to future that seems so obvious to us, is a fundamental feature of reality or an emergent property of something deeper. This question turns out to be intimately connected to the Big Bang, because the Big Bang is, in a precise technical sense, the place from which the direction of time appears to originate, and the puzzle of why time has a direction at all is one of the most genuinely strange problems in modern physics. Let me start with the basic situation. The fundamental laws of physics, as we currently understand them, are almost entirely time-symmetric. By this I mean that the equations governing the behavior of matter and energy work equally well if you reverse the direction of time. A film of two billiard balls colliding looks just as physically valid played forwards as it does played backwards. The equations describing electromagnetic fields, gravitational fields, and the interactions of fundamental particles all share this property. There is no preferred direction of time built into the basic laws. They are, in technical language, invariant under time reversal, with one small and very interesting exception that I will return to in a moment. And yet our experience of time is anything but symmetric. We remember the past, but not the future. Eggs break, but do not unbreak. Hot coffee cools, but cold coffee does not spontaneously heat itself. People age. Buildings decay. Information accumulates in some directions and is lost in others. The arrow of time, as physicists have called it, is among the most universally observed features of reality, and yet it is not present in the fundamental equations that supposedly describe how reality works. Where does the arrow come from? Why does time appear to have a direction in our experience when the underlying physics treats both directions as equally valid? The standard answer, developed primarily through the work of Ludwig Boltzmann in the late 19th century and refined by countless physicists since, locates the arrow of time in a quantity called entropy. Entropy is, roughly speaking, a measure of how disordered a system is, or more precisely, how many different microscopic configurations are compatible with a given macroscopic description. A neat stack of cards has low entropy because there is only one way to arrange the cards in that specific order. A shuffled deck has higher entropy because there are many different shuffled arrangements that all look essentially the same at the macroscopic level. The second law of thermodynamics states that the entropy of an isolated system tends to increase over time, moving from less probable configurations to more probable ones. This is not a fundamental law in the same sense as the laws of mechanics. It is a statistical tendency derived from the simple fact that there are vastly more disordered arrangements than ordered ones, and so a system evolving randomly will, with overwhelming probability, move from order to disorder rather than the reverse. This statistical tendency, applied across the universe as a whole, gives us the arrow of time. The future is the direction of higher entropy. The past is the direction of lower entropy. We remember the past because the formation of memories is itself a process that increases entropy in our brains and our environments, and the only direction in which entropy can have been lower is the direction we call the past. The asymmetry of our experience reflects not a fundamental asymmetry in physical law, but the statistical asymmetry between high entropy and low entropy configurations of complex systems. So far, so good. This is the standard textbook explanation, and it has been refined over more than a century into a sophisticated and largely successful framework. But here is where it gets strange. The statistical argument for the arrow of time only works if the universe started in a low entropy state. If the early universe had been in a high entropy state, then entropy would have nowhere to go but down, and the arrow of time would point in the opposite direction, or, more likely, would not exist as a coherent feature of experience at all. The entire structure of our temporal experience depends on the fact that the universe began in an extraordinarily ordered, low entropy condition, from which it has been increasing in disorder ever since. The Big Bang, in this view, is not just the beginning of the universe in some general sense. It is specifically the beginning of the arrow of time, the source of the asymmetry that gives our existence its forward-flowing character. And here is the puzzle. The early universe, according to our observations, was extremely uniform, extremely smooth, with temperature variations of less than 1 part in 100,000 across the entire observable cosmos. In thermal terms, this looks like a high entropy state, because uniformity is associated with thermal equilibrium, and thermal equilibrium is the maximum entropy condition for a given amount of energy. But when you include gravity in the calculation, the picture changes dramatically. For a system dominated by gravitational interactions, smooth uniform matter is actually a very low entropy state, and the high entropy configurations are the ones in which matter has clumped together into dense structures like black holes. The early universe, despite its smoothness, had extraordinarily low gravitational entropy, and the entire history of cosmic structure formation, with matter collapsing into stars and galaxies and clusters and ultimately into black holes, has been a process of gravitational entropy increase that drives the thermodynamic arrow of time we experience. So the question becomes, why was the early universe in such a low entropy state to begin with? This is a deep and genuinely difficult question, and it does not have a satisfying answer in current physics. The universe, by all accounts, started in a condition of staggering improbability when measured by gravitational entropy, and we do not know why. The standard inflationary cosmology that we discussed earlier provides part of an explanation, in that inflation tends to smooth out initial inhomogeneities and produce the kind of uniform initial conditions we observe. But inflation itself requires a low entropy starting point for its dynamics to work properly, so the question of low initial entropy is pushed back rather than resolved. We are left with the recognition that the universe began in a configuration that was, by any reasonable measure, fantastically ordered, and that everything we experience as the passage of time is the slow unwinding of that initial order into greater and greater disorder. The arrow of time points away from the Big Bang because the Big Bang was the most ordered moment in cosmic history, and we are, in a sense, falling away from it into ever more probable configurations of the matter and energy it set in motion. I want to bring in here the small exception I mentioned earlier to the time symmetry of fundamental laws. There is one specific kind of process in particle physics that does, very slightly, treat the two directions of time differently. This is the same CP violation we encountered in our discussion of the matter-antimatter asymmetry. Certain decays of particles like kaons and B mesons proceed at very slightly different rates depending on the direction of time, and this asymmetry is built into the standard model of particle physics at a fundamental level. The asymmetry is small, and it does not seem to be enough on its own to generate the macroscopic arrow of time we experience. But it is real, and it complicates the simple picture in which all fundamental physics is time symmetric and the arrow of time is purely a statistical phenomenon. There is a small, genuine asymmetry built into the fundamental laws, and physicists have not yet fully worked out how this asymmetry relates to the larger thermodynamic arrow we observe. Now I want to push further into territory that becomes, frankly, quite strange. There is a school of thought in theoretical physics, with serious advocates among careful researchers, that questions whether time is fundamental at all. According to this view, time is not a basic ingredient of reality, but an emergent property of something deeper, in much the way that temperature is an emergent property of the underlying motion of molecules, rather than a fundamental quantity in its own right. The candidates for what time might emerge from include quantum entanglement among the components of a system, geometric structures in higher dimensional spaces, and various forms of computational or informational dynamics that have time-like properties only when viewed in certain ways. These ideas are not yet established physics. They are speculative proposals being explored at the frontiers of theoretical work. But they are taken seriously enough that some of the leading thinkers in cosmology and quantum gravity have devoted significant effort to developing them, and the possibility that time itself might be emergent rather than fundamental is now part of the active discussion in the field. If time is emergent, then the question of what came before the Big Bang takes on a very different character. The question may be malformed in the way that asking what is north of the North Pole is malformed. There may be no before in any meaningful sense, because the conditions under which time can exist may not have applied to whatever was happening at or near the singularity. The universe may not have begun in time. It may have begun with time, in a way that makes the question of prior existence simply not applicable. This is a difficult idea to hold in the mind, because our cognitive apparatus is so deeply structured by temporal experience that we have trouble even imagining what it would mean for time itself to have an origin. But the mathematics, in some of these theoretical frameworks, points in this direction, and the philosophical implications, if the mathematics turns out to be right, are profound. There is also a related question about the future, which mirrors the question about the past. If the arrow of time depends on the universe having started in a low entropy state, what happens when the universe eventually reaches a high entropy state in which no further increase is possible? This is the so-called heat death, the eventual thermal equilibrium of the cosmos in which all useful energy has been dissipated and no further work can be done. In such a state, would time still have a meaningful direction? Would there even be observers around to notice? The standard expectation is that, given enough time, the universe will reach a configuration in which the arrow of time becomes ambiguous or absent, in which fluctuations occur randomly in both directions, and in which the kind of experience we have, with memory and anticipation and the felt flow of moments, becomes impossible. The Big Bang gave us our arrow. The far future will, in some sense, take it back, restoring a kind of temporal symmetry in which the distinction between past and future loses its meaning. What I want you to take from all of this is a sense of how genuinely deep the puzzle of time is, and how connected it is to the puzzle of the Big Bang. The Big Bang is not just the beginning of the universe in the casual sense of being the first event in a sequence. It is, in a more profound sense, the source of the very directionality that makes a sequence of events meaningful. Without the low entropy initial condition that the Big Bang provided, there would be no arrow of time, no flow of moments, no memory of the past or anticipation of the future. The fact that we exist as temporal beings, experiencing the world through the lens of duration and change, is a direct consequence of the cosmos having begun in the specific kind of state that it began in. And this state is not predicted by any deeper theory we possess. It is a brute initial condition, an unexplained starting point from which everything else has flowed. There is something almost mystical about this when you really sit with it, though I do not want to push the language in that direction. The point is more sober than that. The very fact that you can have an experience at all, that there can be a moment which then becomes a previous moment, that there can be a sense of one thing leading to another, depends on a feature of cosmic history that we do not understand. We are temporal beings inhabiting a temporal universe, and the temporality of both us and the universe is a gift from initial conditions that we cannot account for. Every breath you take, every word of this sentence as it unfolds in your awareness, is part of a vast unwinding of order that began with conditions whose origin remains unexplained. The night that surrounds you now is, in this precise sense, a continuation of the first moments of the universe, the same arrow of time still pointing forward through your present experience, all the way from a beginning whose nature we are still trying to comprehend. Picture this as you let your awareness soften further. The universe, immediately after the Big Bang, in a state of extraordinary order whose source is unknown. From this state, everything that has ever happened has been the gradual increase of entropy, the slow movement toward greater disorder. Stars formed out of collapsing gas, ordering some matter into dense, bright structures, while heating the surrounding space and increasing the total disorder of the cosmos. Planets formed from circumstellar disks, ordering some matter into solid bodies, while spreading energy across larger volumes. Life emerged on at least one planet, ordering matter into extraordinarily complex structures, while consuming and dispersing energy at high rates. Consciousness emerged, ordering information into still more complex patterns, while drawing on the gradients of energy that the rest of the cosmos provides. Every act of ordering, every moment of coherent experience, every thought that passes through a mind anywhere in the universe is paid for by an increase in disorder somewhere else in the cosmic system. The price of your present awareness is the gradual exhaustion of the thermodynamic gradient that the Big Bang established. You are, in a literal sense, made possible by the long unwinding of a cosmic initial condition whose origin we cannot account for. I want to take you now into a question that sounds deceptively simple, but that turns out to dissolve into puzzles the moment you examine it carefully. The question is, what was happening before the Big Bang? This question is, in some technical sense, not even well formed within standard cosmology, because the Big Bang is supposed to mark the beginning of time itself, and asking about what came before time began is, as we touched on briefly in the previous part, a bit like asking what is north of the North Pole. There is, on this view, simply no before in any coherent sense, but the question keeps getting asked anyway, and not just by curious children and confused journalists. It gets asked by serious cosmologists who have proposed a remarkable variety of speculative answers, none of which is currently testable, but all of which are taken seriously enough to occupy substantial portions of the technical literature. The reason cosmologists keep returning to this question, despite its apparent ill-formedness, is that the standard framework leaves it strangely unsatisfying. To say that time began with the Big Bang, and that there is therefore no meaningful before, is to give an answer that feels like a refusal to answer. It works mathematically within the equations of general relativity, but it leaves intact the deeper puzzle of why there is a universe at all, and why the universe has the specific properties it has. The various proposed pre-Big Bang scenarios are attempts to address these deeper puzzles by extending the description of reality back beyond the apparent beginning, into a regime where different physics might apply, and where the initial conditions of our cosmic phase might be derived from. Something more fundamental rather than simply postulated. The simplest of these proposals, and one of the oldest, is the cyclic universe model. This idea holds that the universe undergoes an endless series of expansions and contractions, with each Big Bang followed eventually by a big crunch, which then somehow rebounds into a new Big Bang, and so on indefinitely in both directions. The appeal of this model is obvious. It eliminates the question of what came before by positing an infinite past sequence of cosmic phases, each emerging from the collapse of a previous one. The trouble is that the second law of thermodynamics seems to forbid it, because each cycle would, by all standard reasoning, end with higher entropy than it began with, and an infinite past sequence of increasing entropy cycles would have to start from a state of either infinite or undefined entropy at some point in the past. There are sophisticated attempts to handle this problem, including proposals that the inflation in each cycle effectively resets the entropy of the observable patch of universe to a low value, while distributing the accumulated entropy across a vastly expanded volume. Whether these proposals actually work is a matter of ongoing technical debate, but the cyclic universe model has not been dismissed, and serious physicists continue to develop versions of it. A more recent and more elaborate proposal is the ekpyrotic scenario, developed by physicists Paul Steinhardt and Neil Turok, among others. This model draws on string theory and the concept of higher dimensional spaces to propose that what we experience as the Big Bang was actually the result of a collision between two membranes, or branes, in a higher dimensional bulk space. Our entire observable universe, in this picture, is a four-dimensional surface embedded in a larger structure with additional spatial dimensions, and the membrane on which we live periodically collides with a parallel membrane separated from us by a distance in the extra dimensions. Each collision triggers what we perceive as a Big Bang, with the energy of the collision driving the rapid expansion and the subsequent evolution of cosmic structure. The membranes then move apart again, eventually returning toward each other to repeat the cycle. The ekpyrotic model is one of several attempts to use the mathematical apparatus of string theory to address the pre-Big Bang question, and while it remains speculative and has faced various critical challenges, it has been refined over the years and continues to be developed. A still more radical proposal comes from loop quantum cosmology, an application of the Loop Quantum Gravity Research Program to the early universe. According to this approach, space-time is not infinitely divisible, but consists of discrete units at very small scales, much as matter consists of discrete atoms, rather than continuous substance. When you apply this discrete space-time structure to the equations of cosmology, the singularity at the Big Bang is replaced by something called a quantum bounce. Instead of an infinitely dense initial state, the universe at the apparent beginning was in a finite, though extreme condition, having previously contracted from a large size, reached a minimum size dictated by the fundamental graininess of spacetime, and then bounced back into an expanding phase. According to this picture, the universe before the Big Bang was much like the universe today, in the sense that it had stars and galaxies and ordinary cosmic structure, but it was contracting rather than expanding, until quantum gravity effects became important at the smallest scales and reversed the direction of evolution. The Big Bang, in this view, is not a beginning, but a transition, a phase change between a contracting era and the expanding era we now inhabit. Each of these proposals has its supporters and its critics. None of them has any direct observational support, because the conditions they describe are either inaccessible in principle or have left such faint traces in the observable universe that we cannot yet detect them. They remain, in the technical sense, speculative theoretical constructions, motivated by the desire to push our understanding back beyond the apparent beginning, rather than by any compelling empirical reason to believe that they describe reality. And yet, they are taken seriously, developed mathematically, debated in conferences and journals, because the alternative, which is to accept that time and space simply began at the Big Bang for no further reason, feels to many physicists like a refusal to engage with the deepest question that cosmology can ask. Now I want to introduce a different kind of approach to the same problem, because it changes the entire character of the question in interesting ways. There is a research program in quantum cosmology developed primarily by Stephen Hawking and James Hartle in the 1980s that proposes what they called the no-boundary proposal. According to this approach, the question of what came before the Big Bang is not so much wrong as misframed. The proposal uses a mathematical technique in which the time dimension near the apparent beginning of the universe smoothly transforms into something more like a fourth spatial dimension. In this picture, the early universe does not have a sharp beginning at a moment in time, because the very concept of time becomes blurred at the smallest scales and earliest epochs. Instead, the universe has a smooth boundary in a four-dimensional space, much as the surface of the Earth has a smooth shape without any sharp boundary or edge. Asking what came before the Big Bang is then like asking what is south of the South Pole. The question can be formulated, but it does not refer to anything. because the South Pole is the southernmost point and there is nothing south of it in any meaningful sense. The no-boundary proposal is mathematically elegant, and it offers a way of thinking about the beginning of the universe that does not require either an infinite regress of prior phases or an unexplained moment of origin. The universe, in this view, simply is, with a particular four-dimensional shape that includes what we call the Big Bang as one of its features, but without any need for explanation in terms of prior causes. Whether this proposal is actually correct is again not currently testable, and the philosophical implications are slippery enough that even careful thinkers have trouble articulating exactly what it would mean for it to be true. But it represents one of the most serious attempts to address the question of cosmic origin within the framework of mainstream physics, and it has shaped much of the subsequent discussion of these issues. There is yet another approach I want to mention, because it takes the question in a still more unusual direction. Some physicists, drawing on developments in our understanding of quantum mechanics, have proposed that the universe might be in some sense self-explanatory, that the laws of physics might apply not just to the contents of the universe, but also to the universe itself, and that the universe might have come into existence through a process analogous to the spontaneous creation and annihilation of particles that occurs constantly in quantum field theory. According to this view, the universe is, in some technical sense, a quantum fluctuation, a temporary deviation from a more fundamental state of nothingness. Except that the deviation has lasted long enough and grown large enough to contain galaxies and stars and observers. The total energy of the universe, in some accounting, is zero, with the positive energy of matter exactly cancelled by the negative energy of gravitational fields. A universe with zero total energy is, in a certain technical sense, no different from no universe at all from an energy standpoint, and so its appearance from nothing is not necessarily a violation of any conservation law. The mathematics behind this proposal is real and worth taking seriously, but it raises the obvious question of where the laws of quantum mechanics themselves came from, and what kind of nothingness can have laws governing what fluctuations within it are possible. The question of why there is something rather than nothing seems to retreat one step rather than being resolved. What unites all of these proposals is the recognition that the question of cosmic origin is not just a question about what happened at a particular moment, but a question about the deepest structure of reality. The various approaches attempt to address this by extending our description of reality further back, by reformulating the question in terms that make it tractable, or by absorbing the question into a larger framework that includes both the universe and whatever it might have come from. None of them succeeds in producing a complete and verifiable answer, and the question remains, after centuries of philosophical thought and decades of technical cosmological work, fundamentally open. We do not know why there is a universe. We do not know whether the question even has a meaningful answer in any sense we can recognize. We know only that the universe exists, that it has the specific properties we observe, and that the explanations we have for those properties bottom out, eventually, in conditions or principles that we cannot derive from anything more basic. I want to close this part by drawing attention to something that may have struck you as we have gone through these proposals. Each of them, in its own way, is an attempt to push the explanatory regress back one step further to find some deeper level at which the question of cosmic origin becomes tractable. Cyclic models push the question back to the previous cycle. Ekpyrotic models push it back to the dynamics of higher dimensional brains. Loop quantum cosmology pushes it back to a contracting phase before the bounce. The no-boundary proposal pushes it back to a four-dimensional shape that includes the apparent beginning as one of its features. Quantum fluctuation accounts push it back to the laws of quantum mechanics themselves. In every case, the explanation that seems to address the question of why there is a universe ends up itself depending on something else, on prior conditions or fundamental laws or background structures that are themselves not explained. The regress does not terminate. We push it back and back and back, and at every step we find ourselves in need of further explanation, until we either accept some level as a brute fact, requiring no further account, or we admit that we do not know whether the regress can be terminated at all. This may be, in the end, an unavoidable feature of the situation. There may be no way to fully explain why there is something rather than nothing, because any explanation that appeals to existing entities or laws is already presupposing something whose existence stands in need of explanation. The deepest question of cosmology may turn out to be, in a precise sense, an unanswerable question, not because we are too stupid to find the answer, but because the structure of explanation itself does not extend that far. Or it may not. We may eventually find an account that genuinely does terminate the regress, that explains its own foundations, in a way that satisfies whatever criteria of explanation we end up adopting. We do not know, and we cannot know in advance whether we will know. What we can do, and what I have been trying to do tonight, is sit with the question carefully, examine the various approaches that have been taken to it, and recognize the genuine depth of what we are confronting. The Big Bang is not just the beginning of a story that we mostly understand. It is the boundary at which understanding itself becomes uncertain, the place where our explanatory tools begin to fail, the edge beyond which lies either deeper physics that we have not yet discovered, or principled limits on what can be known. Either way, the careful contemplation of that boundary is one of the most genuinely interesting things a thinking creature can do, and it is the kind of contemplation that can occupy a long, quiet night without exhausting its rewards. Picture this, as you let your thoughts continue to slow, a boundary in some unimaginable kind of space, beyond which lies either nothing or something whose nature we cannot describe, and on the near side of which sits everything that has ever been or ever will be in our cosmos. The boundary is not a wall, it is more like a horizon, the place where our descriptions reach their limit, where the categories of before and after, here and there, begin to dissolve into something else. We sit on the inside of this horizon, gazing back toward it through the equations and observations that allow us to reconstruct the early history of our universe, and we do not know what is on the other side, or whether there is another side, or whether the question of another side even has meaning. The horizon is real, and it is permanent, and it is one of the genuinely mysterious features of the existence we find ourselves participating in. Tonight I want to turn from the deep theoretical questions about cosmic origin and take you instead into a question that is, in some ways, even stranger, because it concerns what we can actually see. There is a particular feature of cosmic observation that almost never gets adequately explained in popular accounts. And once you understand it, it changes how you think about the entire enterprise of looking out into the universe. The feature is this: when we look out into space, we are not seeing the universe as it is now. We are seeing the universe as it was at various times in the past, with the depth of the past increasing in proportion to the distance we are looking. The night sky is not a snapshot of the present cosmos. It is a layered tapestry of moments from cosmic history, with each direction we look revealing a different stratum of time. Light travels at a finite speed. This is a fact we all know in some abstract sense, but its implications for astronomical observation are rarely spelled out fully. The light from the moon takes a little over a second to reach us, so when we look at the moon, we see it as it was a second ago. The light from the sun takes about 8 minutes, so the sun we see is the sun of 8 minutes past. The light from the nearest star beyond the sun, Proxima Centauri, takes about 4 years to reach us, so we see it as it was 4 years ago. The light from the bright stars we see in the night sky has been traveling toward us for years to centuries, depending on the star. The light from the Andromeda Galaxy, the most distant object visible to the naked eye under good conditions, has been traveling for about 2.5 million years. So when you look at Andromeda, you see it not as it is now, but as it was when our distant hominid ancestors were just beginning to walk upright on the African savanna. This effect becomes more pronounced as we look at more distant objects. The most distant galaxies that the Hubble Space Telescope and now the James Webb Space Telescope can detect are seen as they were within the first billion years after the Big Bang, when they were young, often irregularly shaped, full of bright young stars, and significantly closer together than galaxies are now. We are not seeing what those galaxies are now. We are seeing what they were more than 12 billion years ago. The current versions of those galaxies, if they still exist in any recognizable form, have been evolving for the past 12 billion years, and we have no way of knowing what they look like in the present moment, because the light from their present moment will not reach us for another 12 billion years, by which time the Earth and Sun will have ceased to exist in any form that could observe it. When we look at the cosmic microwave background, the diffuse glow of radiation that fills the entire sky, we are looking at light that was emitted approximately 380,000 years after the Big Bang. The moment when the universe became transparent to light for the first time. This light has been traveling toward us for nearly the entire history of the cosmos, and the regions of space from which it was emitted are now separated from us by vast distances that the light could not possibly traverse in the time available. We see the early universe as a kind of background curtain at the limit of our cosmic vision, beyond which we cannot see, because before that moment, the universe was an opaque plasma that did not allow light to travel freely. The cosmic microwave background is, in a literal sense, the oldest thing we can ever see. It is the surface of the cosmic horizon, and beyond it lies the period from which no light can reach us, because no light could escape until that moment. This means that astronomy is not a science of looking at distant places, it is a science of looking at distant times. Every observation we make of the cosmos is an observation of the past, with the depth of the past corresponding directly to the distance of the object. We cannot, even in principle, observe the universe as it currently is. We can only observe it as it was at various moments in its history, and the moments we can observe range from the present, in our immediate vicinity, all the way back to nearly the beginning of cosmic time, in the most distant regions accessible to our most sensitive instruments. The night sky, when you really think about it, is not a sky at all. It is a museum of cosmic history, with each exhibit showing the universe at a different stage of its development, all of them visible simultaneously in different directions and at different distances. This has some consequences that are deeply strange when you sit with them. The first is that the universe, as a whole, may not have a well-defined present moment in any sense that we can observe. Different parts of the cosmos are moving in different directions and have been doing so for various lengths of cosmic time, and the relativity of simultaneity, established by Einstein more than a century ago, tells us that there is no universal answer to the question of what is happening right now in distant regions of space. The concept of now, applied to the cosmos as a whole, is not just impractical to determine. It may be physically meaningless beyond a certain scale. We exist in a kind of perpetual past tense, observing a universe that exists for us only in fragments of various ages, with no way to access any unified present that would tie all of those fragments together. The second consequence is that the universe we see, in some important sense, is no longer there. The galaxies whose light has been traveling for 12 billion years to reach our telescopes have continued to evolve, to interact with their neighbors, to form new stars, to perhaps merge or be torn apart by tidal forces, to create black holes and supernovae and all the other transformations that galactic evolution produces. The light we are now detecting was emitted by structures that, in the present moment of those distant locations, no longer exist in the form we are observing them. Astronomy is, in this sense, the study of cosmic ghosts, of structures whose past selves we can see, but whose present selves we cannot reach. The night sky is haunted by the light of objects that, by now, are different objects entirely. The third consequence, and perhaps the most striking, is that the structure of cosmic observation gives us a kind of access to the early universe that we do not have to any other period of natural history. When we look at the Earth, we see it as it is now. When we want to know about the Earth's past, we have to dig up evidence of past states, fossils and rock layers and ice cores, and reconstruct the past from the residual evidence available in the present. But when we look at the cosmos, we directly observe the past. We do not need to reconstruct it from indirect evidence. We can see, with our actual instruments, the universe as it was at various moments, stretching back nearly to the beginning. This is a unique kind of access to history, and it has allowed cosmology to develop into one of the most precise of the historical sciences. Because we can compare our theoretical predictions about the early universe against direct observations of the early universe, rather than having to infer the past from its surviving fragments in the present. But this access has limits, and the limits are themselves interesting. We can see back to the cosmic microwave background, which represents the universe at about 380,000 years of age. We cannot see further back than that with electromagnetic radiation, because before that moment, the universe was opaque. There is, however, the possibility of seeing further back through other means. Gravitational waves, ripples in the fabric of space-time itself, are not absorbed by the early dense plasma the way electromagnetic radiation was, and they could in principle carry information from much earlier moments, perhaps even from the inflationary era or from whatever process gave rise to inflation in the first place. Neutrinos, which interact extremely weakly with ordinary matter, could similarly carry information from earlier epochs than the cosmic microwave background. Detection of either of these primordial signals is currently beyond our capabilities, but it represents a real possibility for future observations, and the search for cosmic gravitational wave backgrounds is one of the active frontiers of contemporary cosmology. There is also a limit on how far we can see in any direction, regardless of the medium of observation. The observable universe is bounded by what is called the particle horizon, the maximum distance from which light could have reached us in the time available since the Big Bang. This horizon is currently about 46 billion light-years in radius, which is larger than the simple product of the speed of light and the age of the universe, because the universe has been expanding during the entire time the light has been traveling, stretching the actual distance to the source. Beyond this horizon, there may be more universe, possibly an enormous amount more, possibly an infinite amount more, but we cannot observe it because no signal from it has had time to reach us. We are confined, observationally, to the volume of space from which light has had time to arrive, and this volume is finite and bounded, even if the underlying universe extends much further or even forever. This raises a question that may be impossible to answer. What is beyond the observable universe? The honest answer is that we do not know, and we may never know, because the regions beyond our particle horizon are causally disconnected from us, in the sense that no information from them can reach us within the lifetime of our cosmos. There are theoretical reasons to believe that the universe extends well beyond our observable horizon, perhaps far enough that it is functionally infinite. Inflation, if it occurred, almost certainly produced a universe much larger than the observable region. The flatness of the geometry of the universe, which we can measure with reasonable precision, is consistent with a universe that is either spatially infinite or at least very large compared to the observable region. But these are theoretical inferences, not direct observations, and the question of what the unobservable parts of the universe are actually like is, and probably will always remain, beyond our empirical reach. I want to bring in here a related and somewhat unsettling consequence of our observational situation. The expansion of the universe is accelerating, as we discussed in an earlier part. This acceleration means that, over time, distant galaxies are receding from us faster and faster, and eventually, their recession velocities will exceed the speed of light, at which point they will effectively disappear from our cosmic view. The observable universe is, in a real sense, shrinking with cosmic time, as more and more of it crosses outside our event horizon and becomes inaccessible. Far enough into the future, in trillions of years, observers on whatever planets still support intelligent life will look out at a sky that contains only the galaxies of their own local cluster, with all other galaxies having receded beyond their horizon. They will see no cosmic microwave background, because the radiation will have been redshifted to undetectable wavelengths. They will have no observational access to the Big Bang, no evidence of the larger cosmic structure, no way to know that the universe they inhabit is anything other than a small island of galaxies in an apparently empty void. They will be cosmologically isolated, with no way to reconstruct the cosmic history that we can currently see. This thought, which has been developed by various cosmologists, including Lawrence Krauss and Robert Scherer, has a kind of vertigo to it. We happen to live in an era when the universe is observable in a way that future eras will not be. The history of the cosmos is, for us, accessible to scientific investigation, with the cosmic microwave background and the distant galaxies still visible and the expansion still measurable. In the deep future, this accessibility will be lost. The universe will become, for any future observers, a much smaller and more impoverished place, with no evidence remaining of its larger context. We exist in a cosmological golden age, and we did not choose this. It is simply when we happen to find ourselves in cosmic history. Whether other intelligent species, distributed across other galaxies, are observing this same era or different eras depends on factors we cannot determine, but for any given observer in any given galaxy, the window for cosmological observation is finite, and we are inside that window now while it remains open. What I want to leave you with from this part of our exploration is a heightened appreciation for the strange and privileged nature of our observational position. We are looking out at a cosmos in a particular moment of its history, when the structures we see are still close enough to be visible, when the cosmic microwave background is still present, when the expansion has not yet carried distant galaxies beyond our horizon. The universe we observe is not the universe of all times. It is the universe of our era, and the era is characterized by specific observational possibilities that did not exist in the deep past and will not exist in the deep future. Every photon that reaches your eyes from the night sky has been traveling for a length of time that depends on the distance of its source. And the photons together compose a portrait of cosmic history that is itself a temporary artifact of where we happen to be in cosmic evolution. The picture you see when you look up is not the universe, it is a slice through the universe, a particular cross-section of cosmic space-time, available to us only because we exist when we exist and where we exist. I want to spend tonight on a question that quietly underlies everything we have been examining, but that we have not yet addressed directly. The question concerns the relationship between mathematics and physical reality, and specifically why the universe seems to be describable by mathematics at all. This may sound abstract or philosophical, but it turns out to be one of the most genuinely puzzling features of the cosmos we inhabit, and it has profound implications for how we should interpret the entire enterprise of scientific cosmology, including everything we have said about the Big Bang and its consequences. Let me start with the basic observation. Modern physics is fundamentally mathematical. The laws of nature are expressed as equations, and the equations make precise quantitative predictions that experiments and observations consistently confirm to extraordinary precision. This is true across all the major branches of physics. General relativity is a set of mathematical equations that describe the geometry of space-time in terms of the distribution of matter and energy. Quantum field theory is a mathematical framework that describes the behavior of fundamental particles in terms of operator-valued fields acting on abstract Hilbert spaces. Statistical mechanics derives the macroscopic properties of matter from mathematical analyses of probability distributions over microscopic configurations. The standard model of particle physics is a specific mathematical structure with 20 or so adjustable parameters that, once fixed, predicts an enormous range of phenomena with precision that often exceeds the experimental capabilities of measuring them. This mathematical character of physics is so familiar to us that we rarely stop to ask why it is the case. The physicist Eugene Wigner, in a famous essay published in 1960, called this the unreasonable effectiveness of mathematics in the natural sciences, and he argued that it is genuinely mysterious. Why should the universe be describable by mathematical equations at all? Mathematics, after all, is something that human beings developed primarily for purposes other than describing the cosmos. It originated in counting and measuring and the practical needs of agriculture and trade. Geometry was developed for surveying land, algebra for solving problems in commerce and astronomy, calculus for handling rates of change in mechanical systems. The various more abstract branches of mathematics were developed for reasons internal to mathematics itself, with no particular regard for whether they would turn out to describe physical reality. And yet, again and again across the history of physics, mathematical structures developed for purely abstract reasons have turned out to be exactly the right tool for describing aspects of the physical world that nobody had even conceived of when the mathematics was first developed. Riemannian geometry, an elaborate mathematical theory of curved spaces in arbitrary numbers of dimensions, was developed by mathematicians in the 19th century as a generalization of ordinary geometry, with no application in mind beyond pure mathematics. Half a century later, Einstein realized that Riemannian geometry was exactly the framework needed to express his theory of general relativity, in which gravity is interpreted as the curvature of four-dimensional spacetime. The mathematics that Einstein needed to formulate the most accurate theory of gravity we possess had already been developed, decades earlier, by mathematicians who had no idea anyone would ever use it for physics. The same pattern has occurred repeatedly. Group theory, an abstract mathematical structure for analyzing symmetries, was developed in the 19th century for reasons entirely internal to mathematics. In the 20th century, it became the central tool for understanding the symmetries that govern fundamental particles and their interactions. The standard model of particle physics is, in a precise technical sense, an application of group theory to the fields that describe matter and forces. Without the abstract mathematical work that had been done long before particle physics was even a discipline, the modern theoretical understanding of the subatomic world would not have been possible. Hilbert spaces, infinite dimensional vector spaces with specific mathematical properties, were developed in the early 20th century as a generalization of ordinary geometry. They turned out, almost immediately afterward, to be exactly the right framework for formulating quantum mechanics, in which the state of a physical system is represented as a vector in such a space. The mathematical structure had been worked out for abstract reasons. The physical theory needed it, and there it was, ready to be used. This kind of coincidence, repeated across so many areas of physics, is what Wigner found unreasonable. The universe should not, on any naive expectation, be so consistently and so precisely describable by mathematics that human beings have developed for entirely independent reasons. There are several possible interpretations of this strange fact, and each of them has interesting implications. The first interpretation is that the effectiveness of mathematics is not really unreasonable, but only seems so. According to this view, mathematics is so general and so flexible that given any structured phenomenon in the world, some piece of mathematics will turn out to fit it. The cases where the fit is striking are remembered, while the cases where mathematics has not yet found application are simply forgotten. This is a deflationary interpretation, and it has the merit of avoiding metaphysical claims, but it does not really account for the precision and the depth of the matches we observe. When general relativity predicts the orbital precession of Mercury to 4 decimal places of precision, it is hard to attribute this to a generic flexibility of mathematics. Some specific feature of the world is being captured by the equations, and the capturing is far too tight to be attributed to coincidence. The second interpretation is that mathematics is effective because the universe is, in some deep sense, mathematical in nature. According to this view, the structures we discover when we do mathematics are not merely useful tools for describing reality, but are themselves elements of reality. The mathematical relationships that hold in the world hold because the world is, fundamentally, a mathematical structure. This idea has a long history, going back at least to Plato and Pythagoras, and it has been advocated in various forms by serious modern thinkers, including the physicist Max Tegmark, who has proposed what he calls the mathematical universe hypothesis. According to Tegmark, every consistent mathematical structure exists in the same sense that our universe exists, and our universe is one such structure, no more or less real than the others. Physical reality and mathematical reality are, on this view, the same thing, and the effectiveness of mathematics in describing the world is not a coincidence, but a tautology. This is a striking proposal, and it has the virtue of explaining why mathematics works so well as a tool for understanding the world. But it raises a host of further questions. Which mathematical structures correspond to actual universes and which are merely abstract possibilities? Is there a difference, on this view, between existence and non-existence, or do all consistent mathematical structures exist equally? Why do we find ourselves in this particular mathematical structure rather than some other one? The proposal seems to require something like the multiverse interpretation we discussed earlier, with our universe being one element in a vastly larger ensemble of mathematical possibilities, each of them as real as any other. Whether this constitutes a satisfying explanation or simply a redescription of the puzzle in different language is a matter of philosophical taste. The third interpretation is intermediate between these extremes, and it is the one that I find personally most plausible, though I want to emphasize that this is not a settled question and that thoughtful people disagree. According to this view, mathematics is effective because both mathematics and the physical world share a common feature, namely structure. Mathematics studies structures in their pure form, abstracted from any particular physical realization. The physical world contains structures, instantiated in matter and energy and space-time. The structures in the physical world happen to be of kinds that mathematics can describe, because mathematics is, in some sense, the science of structure as such. This view does not require either a deflationary dismissal of the puzzle or a metaphysical commitment to a literal mathematical universe. It locates the explanation in the recognition that structure is something we can investigate both abstractly and concretely, and that the abstract investigation, when carried out carefully, will tend to discover the same patterns that show up in the concrete investigation, because the patterns are the same patterns. But even this intermediate view leaves the deeper question unanswered. Why does the world have the kind of structure that allows for mathematical description at all? Why is the universe describable by relatively simple equations, with a small number of fundamental constants and a manageable number of basic principles, rather than being a chaotic mess of unrepeatable phenomena that no mathematical framework could capture? The simplicity and lawfulness of the universe is not a logical necessity. We can imagine universes that would be simply too disordered or too irregular to admit of any mathematical treatment, and yet we do not find ourselves in such a universe. We find ourselves in a universe that, despite its extraordinary complexity at the level of detailed phenomena, is governed at the deepest level by a small number of beautifully elegant mathematical principles. This is itself a fact that requires explanation, and the explanations we have for it are again partial and unsatisfying. I want to bring this back to the cosmological themes we have been developing throughout this exploration. The Big Bang, as a mathematical solution to the equations of general relativity, has the precision and elegance that has come to characterize all the most successful theories in physics. The equations describe the evolution of the cosmos with such accuracy that the predictions match observations to many decimal places, and the underlying mathematical structure has a kind of austere beauty that physicists find compelling. But the equations themselves were derived from very general principles. Principles that Einstein and his contemporaries arrived at through a combination of mathematical analysis and physical intuition. And the universe seems to obey these principles with remarkable fidelity. We did not impose mathematics on the universe. We discovered that the universe was already mathematical, in some sense that we are still trying to understand. This has implications for how we should think about the various unanswered questions we have been examining. The fine-tuning of the fundamental constants is not just a problem about specific numerical values. It is also a problem about why the universe has fundamental constants at all, why the underlying structure can be parameterized by a small number of values that capture its essential features. The matter-antimatter asymmetry is not just a problem about an imbalance in particle counts. It is also a problem about why the underlying physics has the symmetry properties it has, properties that are themselves expressed in elegant mathematical form. The arrow of time is not just a problem about thermodynamic gradients. It is also a problem about why the underlying laws have the time-symmetric structure that makes the existence of an arrow puzzling in the first place. In each case, the problem we encounter when we examine the universe carefully turns out to be, at least in part, a problem about why the universe has a mathematically tractable structure that allows the problem to be formulated. There is a kind of spiral here that I want to draw your attention to. We use mathematics to investigate the world. We discover patterns and laws and constants. We find that the patterns require explanation, and we use further mathematics to seek the explanations. The further mathematics generates new patterns and new laws, which in turn require further explanation. The process does not terminate in any obvious way. Each level of mathematical description seems to point to a further level beneath it, with the result that the universe appears to be structured by mathematics all the way down, with no obvious bottom level at which we can simply stop and accept the description as final. Whether this is a feature of reality or a feature of how we approach reality is an open question. Either way, the mathematical character of the universe is one of its most striking and least understood properties, and any complete account of why there is a universe and why it is the way it is would have to include an account of why the universe is mathematical. There is one more thought I want to leave you with before we close this part of our exploration. The development of mathematics by human beings has been, by any reasonable measure, one of the most extraordinary cognitive achievements in the history of life on this planet. We are, as far as we know, the only species that has developed the capacity for abstract mathematical thought. Other animals show varying degrees of numerical cognition, but none, as far as we can tell, develops the kind of formal symbolic mathematics that has allowed our species to formulate the laws of physics and to apply them to the structure of the cosmos. The fact that this cognitive capacity exists at all, that it has developed in a species that originated through a long process of biological evolution on a small planet around an unremarkable star, is itself something of a puzzle. Why should evolution have produced creatures capable of doing pure mathematics? The capacity does not seem to have direct survival value. There is no obvious evolutionary pressure toward developing the ability to do abstract algebra or differential geometry. And yet here we are, doing exactly that, and finding that the abstract mathematics we develop turns out to describe the deepest structure of physical reality. This may be, in the end, the deepest mystery we have encountered tonight. The universe is mathematical. Our minds, products of biological evolution within that universe, are capable of doing mathematics. The mathematics we do turns out to describe the universe with extraordinary precision. The whole arrangement is so neat that it almost seems designed for our comprehension, and yet we have no reason to believe it was designed at all. We are creatures of the cosmos, made of the same atoms as everything else, governed by the same physical laws, embedded in the same evolutionary history that has produced everything else on our planet. And somehow, through the long contingent process of biological development, we have ended up with the cognitive capacity to investigate the deepest structures of the reality we are part of. This is either a remarkable coincidence or a sign of something we do not yet understand about the relationship between minds and the cosmos that contains them, or both. The careful sitting with this question, more than any answer we might give to it, is one of the genuine pleasures available to a thinking creature on a quiet night, and it is a pleasure worth lingering with as our exploration moves toward its conclusion. We come now to the closing part of our exploration, and I want to use it to draw together the threads we have been following across these many hours of slow, careful examination, and to leave you with a sense of what it actually means to live in the kind of universe we have been describing. Because the cumulative weight of everything we have discussed tonight, taken together, points toward a picture of cosmic reality that is far stranger and far more genuinely mysterious than the popular accounts of the Big Bang would lead anyone to suspect. And the strangeness has consequences for how we should think about ourselves and our place in this enormous puzzle. Let us take stock of what we have actually examined. We began with the observation that the Big Bang, as a theory, does not actually describe the moment of cosmic origin, but only the period after the universe was already very small and very hot, with the actual 0 point of cosmic time being a place where our equations break down, and our understanding fails. We saw that the standard model of cosmology requires a hypothetical period of inflation in the very early universe. A period whose mechanism we do not understand and whose consequences seem to imply the existence of vast regions of reality beyond our observable horizon. We examined the apparent fine-tuning of the fundamental constants of physics, the surprising fact that the values of these constants fall within narrow windows that allow for the development of complex structure and life, with no compelling explanation yet available for why this is the case. We considered the matter-antimatter asymmetry, the unexplained imbalance that allowed any matter to survive the great annihilation in the early universe, and that ultimately made our existence possible. We turned then to dark matter and dark energy, the two enormous unknowns that together account for approximately 95% of the contents of the cosmos, and whose actual physical nature has resisted decades of investigation. We explored the puzzle of time itself, the mysterious arrow that gives our experience its forward-flowing character, and that seems to depend on initial conditions of the universe that we cannot derive from any deeper principle. We examined various proposals for what might have come before the Big Bang, including cyclic models and ekpyrotic scenarios and quantum bounces, and no boundary proposals, none of which has achieved decisive support, and all of which raise as many questions as they answer. We considered the strange nature of cosmic observation, the way our telescopes show us the universe at various moments in its history rather than as it is now, and the observational privilege of our particular cosmic era, which will not last, and which future observers will not share. And we took up the deep question of why the universe is mathematical at all, why the cosmos can be described by elegant equations developed for purely abstract reasons, and what this might mean for the relationship between minds and the reality they investigate. Each of these topics, taken individually, is interesting. Taken together, they form a picture that I want to articulate carefully now, because the picture is both sober and remarkable. The picture is that we live in a universe that we partially understand, in some specific and well-defined ways extraordinarily well, and in other equally important ways not at all. The understanding we have is genuine, and the precision of our predictions in their proper domains is among the great achievements of the human intellect. but the boundaries of our understanding are clearly visible, and at those boundaries, the questions we encounter are among the deepest that any thinking creature has ever asked. Why is there something rather than nothing? Why does the universe have the specific properties it has? What is most of the universe actually made of? What gives time its direction? What was happening, if anything, before the moment we call the beginning? Why is the cosmos describable by mathematics? We do not know the answers to these questions. We have proposed answers, and the proposals are sometimes elaborate and mathematically sophisticated, but the proposals have not been confirmed and may never be confirmed, and the questions remain genuinely open. This situation is, I want to suggest, not a failure of the scientific enterprise, but a feature of it. The questions we are encountering at the boundaries of cosmology are not questions that scientists have been negligent in answering. They are questions that may, in some cases, be unanswerable in principle, and in other cases, require theoretical frameworks and observational technologies that we have not yet developed and may never develop. The scientific picture of the cosmos is not a complete picture, and the parts of it that remain incomplete are often the parts that touch on the most fundamental issues about why the universe exists at all and what kind of place it is. This recognition, when you sit with it carefully, is a kind of intellectual honesty that the popular accounts of cosmology often lack. The universe is genuinely mysterious. The mysteries are real, not artifacts of our temporary ignorance, and the long, careful contemplation of them is one of the legitimate occupations of a thinking creature aware of its situation. What does it mean to live in such a universe? I want to offer some reflections on this question, not as conclusions, but as starting points for whatever further thinking you may want to do as you drift towards sleep tonight or in the days ahead. The first reflection is that we exist in a context whose larger meaning, if it has any, we do not understand. The cosmos we inhabit is vastly larger than we can directly observe, vastly older than any human institution, vastly more complex than any single mind can comprehend. We are, by any reasonable measure, very small participants in something very big, and the bigness extends in directions both spatial and temporal that exceed our cognitive grasp. This could be experienced as terrifying, or as humbling, or as oddly liberating, depending on temperament and disposition. The bare fact of cosmic disproportion is not, in itself, an argument for any particular emotional response, but the response, whatever it is, should at least be informed by accurate awareness of the actual situation, rather than by the comfortable illusion that we are at the center of a cosmos that we mostly understand. The second reflection is that, despite the enormous scale and apparent indifference of the cosmos, we have managed to figure out a great deal of what is going on. We have determined the age of the universe to within a few percent. We have measured the rate of cosmic expansion. We have mapped the composition of matter and energy. We have detected the radiation left over from the first transparent moment after the Big Bang. We have observed the formation of structure across cosmic history. We have tested the predictions of general relativity in regimes ranging from the orbits of planets to the merging of black holes. And we have constructed a standard model of particle physics that accounts for the behavior of fundamental matter to extraordinary precision. None of this is small. The cognitive achievement of working out as much as we have worked out, starting from the observational position of small mammals on a single planet around a single star, is perhaps the most remarkable intellectual accomplishment in the history of life on Earth. We should not, in our humility about what we do not know, lose sight of the genuine grandeur of what we do know. The third reflection concerns the relationship between scientific knowledge and the kind of larger questions that scientific knowledge does not directly address. The Big Bang and its associated puzzles touch questions that have, throughout human history, been the domain of philosophy and religion. Why is there something rather than nothing? What is the meaning of existence? What kind of world do we live in? Science, in its careful and limited way, has made remarkable progress on the technical aspects of these questions, narrowing the space of possible answers and providing detailed accounts of the cosmos within its observable scope. But science has not, and probably cannot, definitively settle the larger philosophical questions that surround its findings. Whether the universe means anything beyond itself, whether human existence has any larger significance, whether the cosmos was in any sense intended or designed or merely arose from no cause at all, are questions that the available scientific evidence does not decisively resolve. People come to different conclusions on these matters based on the same evidence, and the conclusions reflect not just differences in scientific reasoning, but differences in deeper intellectual and emotional dispositions. What I want to emphasize is that the openness of these larger questions is not, in itself, an argument for any particular answer. It is simply a recognition that the available evidence underdetermines the conclusions and that thoughtful people can disagree about what the evidence ultimately means. The honest intellectual position, whatever specific conclusions one draws, is to recognize the limits of what can be definitively established and to hold one's deeper commitments with appropriate humility. The universe we have been describing is genuinely mysterious, and the mystery is not going to be dispelled by any straightforward argument or observation we currently possess. The mystery is part of the situation we find ourselves in, and the mature response to it is to engage with it carefully, rather than to paper over it with either confident dismissal or confident assertion. I want to bring this back, finally, to the specific texture of your experience as you have been listening tonight. You are a particular instance of cosmic structure, organized into a body that contains atoms, forged in the cores of long-dead stars and dispersed by supernovae billions of years ago. The energy that maintains your awareness right now flows down a thermodynamic gradient that ultimately traces back to the low entropy initial conditions of the Big Bang. The neurons that are processing the words you are hearing are firing according to electrochemical patterns governed by the same physical laws that govern galaxies. The very fact that you can have an experience at all, that there can be a moment of conscious awareness in which the words of this script appear and are understood, depends on a configuration of cosmic conditions whose origin we cannot fully account for, whose larger context we cannot fully observe, and whose ultimate explanation, if any exists, lies beyond the current reach of human knowledge. You are, in this sense, a participant in the cosmos rather than a mere observer of it. The universe is not something out there that you look at from a position outside. You are inside it, made of it, governed by the same laws that govern everything else, and yet capable of stepping back in thought and contemplating the whole arrangement. This capacity for contemplation is itself one of the remarkable phenomena that the universe somehow makes possible, and the careful exercise of this capacity in long quiet hours like the one you are spending now is among the most worthy uses of conscious experience that I can think of. You are not just a passive recipient of cosmic processes. You are a place where the cosmos becomes aware of itself, however partially and however briefly. The questions we have been examining tonight are questions that the cosmos is, through us and other minds like ours, asking about its own nature and origin. The asking does not yet have answers, and may never have complete answers, but the asking itself is part of what we are here for. There is one final thought I want to leave you with as we close this exploration. The questions we have been sitting with tonight are not new questions. They have been asked in various forms by every generation of thinking humans who have been able to lift their attention from immediate practical concerns long enough to wonder about the larger context of their existence. Ancient Greek philosophers asked them. Medieval theologians asked them. Modern scientists ask them, with the additional advantage of vastly more refined observational and theoretical tools. What is striking is that, despite the enormous progress we have made in answering many specific subsidiary questions, the deepest questions remain essentially unchanged. Why is there something rather than nothing? What kind of cosmos is this? What is our place in it? These questions persist across generations and cultures, suggesting that they touch something fundamental about what it means to be the kind of creature capable of asking questions at all. You are part of that long lineage of questioners. The fact that you have spent this evening sitting with these questions, listening carefully, thinking along with the careful exposition of what we know and what we do not know, places you in a tradition that stretches back as far as human consciousness itself. The questions will continue to be asked after you and I are both gone, by people we will never meet, in cosmic conditions we cannot foresee. The asking is part of the long conversation that thinking creatures conduct with their own existence, and the conversation has no obvious endpoint. What we can do, in our small portion of the conversation, is contribute carefully and honestly, attend to what is actually known and what is not, and pass along to whoever comes after us a slightly more refined understanding of where the genuine questions still lie. That is what cosmology has been doing for the past century. It is what these long, quiet evenings of thinking are for. If you have found this exploration valuable, if the patient walk through the puzzles of cosmic origin and structure has given you something worth carrying into your sleep tonight or your thinking tomorrow, please consider letting me know in the comments below. Subscribe to Sleepy Tinfoil Hat if the channel is the kind of thing you want more of, because the channel grows when listeners tell the algorithm we are here. And tell me, if you are willing, what struck you most in tonight's exploration? What questions you would like to hear more about? What other deep mysteries you would like to spend a long, quiet night sitting with? The audience for this kind of slow, careful inquiry is scattered across many different time zones and many different lives, and the small acts of comment and subscription are how we find each other and keep this work going. Sleep well. Think carefully. The universe is large, and the questions it raises are deep, and the careful sitting with them is one of the few activities that genuinely connects us to the cosmos we are part of. The night that surrounds you is the same night that has held all the questioners who came before you, and that will hold all the questioners who come after. We are, all of us, looking up at the same vast, strange, beautiful arrangement. And the looking is itself a kind of communion with everything we do not yet understand. That brings our exploration to its close. Thank you for staying with me through all 10 parts. If you would like another script in the same patient style on a different topic, I am ready when you are.